Good afternoon and good evening, everybody. We are starting the special session which we are doing with Liverpool John Moores University on artificial intelligence in eye care. And we have two interesting topics today related to a very important area on how to read and understand an artificial intelligence papers, because nowadays we have a pandemic of papers in artificial intelligence in healthcare and eye care. So we need to really understand how to read these papers, so that we need to know which paper really adds value for us and which can be also kind of closely watched for its future. So it's very important to know that. And we have our senior speaker and also the program coordinator, Gabriela, who has been partnering with us in artificial intelligence related to glaucoma from the Liverpool John Moores University. She's going to talk about a typical structure which an AI paper needs and what is normally they apply as a typical structure. Gabriela, please.
Thank you. So I will share the screen. Share. Can you enable sharing of the screen for me?
Yeah, try now, Gabriela.
Yes. Okay, I can see that. Okay, can you see that?
Not yet.
Not
Can you just close it and then reshare?
Okay. Share.
Yeah, now it's starting.
Now you can see it.
Yeah.
And I put it on slideshow. So, can I start?
Yes, please.
Okay. So I will be talking about how do we read and understand AI papers and what is the typical structure of the AI paper. And as Dr. Venkatesh said, we have a tsunami, a large number of papers that are being published. And it is quite intricate to understand what is the structure and how do we read it and how to make sense of it. The how to read papers is something that I already have been presenting in other places, and is also presented by the group of statisticians that I belong to in UK, and that group is called Ophthalmic Statistics Group. It's a national group of people who are statisticians. We also have members from other countries, and we are coming together to make sure that we raise quality of statistics in ophthalmic publications. And also very recently, we are also looking and discussing the issues around how AI should be published and how do we understand those papers. So just a very little to say about the group is that we also do workshops for example, ARVO 1 year. We also do regular trainings for Royal College of Ophthalmologists, and here is our website. And the notes, the slides that I'm going to present here, they are very inspired by the teachings that we did in the past. Also, we are publishing very simple papers called Ophthalmic Statistics Notes in BGO Journal for those who are very new in statistics. So what do we mean by AI paper, or what do I mean by AI paper? By AI paper, I mean any paper that has artificial intelligence component in it. And what I mean by that is that there has been a computer algorithm designed, and this computer algorithm does some tasks automatically. It can either automatically detect disease. So this is something like we discussed last week, how to take image of the retina, put it into algorithm, and this computer algorithm will tell us whether it is glaucoma or not. Okay, so this can be done by deep learning, or we can have other algorithms that involve more steps on the way. Or it can be a paper that contains computer algorithm that automatically quantifies some aspects of the ophthalmic data. So here is an example. We looked into capillary non-perfusion in fluorescein angiography photography in children who have malarial retinopathy. And there was a computer algorithm who would take the image, which is here, the FA image, the fluorescein angiography. This algorithm will use some mathematical principle to denoise the image and deblur it to make the features, the vessels, more visible and distinct. Okay, this can then be used by clinicians to manually evaluate, for example, how much capillary non-perfusion is there, or you can use further mathematical algorithm to do automated feature segmentation, like you see here with these red areas. And these red areas here, they are indicating the boundaries of capillary non-perfusion. Of course, we made assumption that if the image appears black, that's the area where the vessels are not there anymore, the capillaries are not there anymore, and we are making assumption that there is a non-perfusion, okay? And then we can quantify, we can then say, okay, how many pixels are there that are capillary non-perfused, and are they mainly happening in the temporal area, or is in the superior area, etc. And we can even do it in a statistical way, for example. Okay, so this is also AI, even though it doesn't give diagnosis, but rather it only, well, it tells us where the capillary non-perfusion is. Okay, or here it tells us, it gives us a better visual presentation where the capillaries are and where they are not. So these are the two types of papers, I would say, where we see some computationally intensive components, what I call AI. So these AI papers, they do come with various technical complexities. They can be either very technical, so there is lots of mathematical and computational element. There may be machine learning in it, statistical models, they may be in it. These papers are typically published in technical journals. And they typically are validated, the AI is typically validated on online data or retrospective data. Typically, the sample size may be smaller, and typically it's internal validation where the data set is split into two halves, one for training, one for testing. And typically, after a group publishes a technical paper, they would then go onto publishing a more clinical paper where technical detail may be omitted, referring to the more technical paper. And now they are more focusing on the clinical validity of the AI. So for example, they may now more typically use prospective or clinical trials data. The sample size you may see may be bigger, and they may even do external validation, but again, typically, okay? So why do clinicians, ophthalmologists need to know how to read a clinical paper that contains AI? There are three reasons. You to understand the papers and to know how to clinically appraise them. You need to know whether this paper is giving you any suggestion that you need to change practice, for example, the way we diagnose, follow, or treat patients. Or you may be a reviewer, and the question is, how do you start? There is also another type of reviews that people do, and they are called systematic reviews, but I will not talk about these here. But for those who are interested on what systematic reviews are, there is this, for example, Cochrane Eye and Vision Group, where they have lots of training and information how to do those. So what is a typical ophthalmic paper that contain AI elements? What is the structure? The structure is the same as any other paper, and that would be, it has a title. Typically in title, there will be an indication whether there was AI used or not. There will be abstract, introduction, methods, results, and discussion. And the structure will be very much the same as any papers that are published that do not use AI. What I would stress here is that AI may appear in the methods. Of course, there will be some description, of the AI methods, or the details will be referred to other previously published paper where the details are already published. Then you will see AI in results, of course. For example, the validation of the AI will be there. And then very importantly, in discussion, there needs to be some discussion as to how successful AI was, and also whether there are any limitations. So this is a very busy slide, but it is the most important slide. And this is the way how is useful, I think, to think about when reading a paper that contains AI. And that is, the most important part is the research question. That's why I put it into very bright yellow. The research question can be either automated diagnosis of glaucoma, or automated segmentation of capillary non-perfusion, okay, and then learning whether this capillary non-perfusion is in any way associated with the death of the patient or not, okay. So that's the most important part. Is the research question clear in the paper? And this research question, where do you find it? You will find it a little bit in the title. You will find it also a little bit in the abstract, but most importantly, it will always need to be as a very last paragraph in introduction. There in introduction, it should be very, very clear. And if it is not clear, then something is not working well. So in the very last paragraph of introduction, people would either write a research question, they would also write a very specific objectives. And if it is relevant, they would also write down hypotheses, if it is, for example, a confirmatory study. Okay. So once you understand the research question, then you need to understand what are the population, what is the population of patients that the paper is talking about, what design they are using, is it a prospective, retrospective study, okay, how do they measure the variables, okay, and what data analysis methods they are using. So this will be all in this green circle, which I call the methods section. And in this method section, there are two tricky parts. One is the AI may be involved in the measurement. For example, in the measurement of the capillary non-perfusion, okay? Or AI may be involved in the actual diagnosis, okay? Like the automated glaucoma diagnosis. So this can be the tricky part. Then there will be a results and discussion. And of course, the question is whether the AI involved has been reported accurately. This is again a tricky part. And this is very much the area of still discussions and discussions between all involved, the statisticians, clinicians, about how AI should be reported. And there is an increasing number of papers that are being published on how AI should be reported in clinical papers. And also, very importantly, this finer last green circle, which is the paper that I'm reading showing something that it was feasible to do? Is it interesting for me? For example, interesting for my patients and my practice? Is it novel? Is it ethical what they did, and is it relevant? But when I read a paper and I stop understanding, I go back to the research question, because that's always the starting point. So, for example, AI can be used to provide measurements from retina to study associations. Okay, so I'm showing here an example of paper that we published in Liverpool with Ian McCormick being the first author in Scientific Reports 2017. And the research question was, is there an association between the death and survival of a child and the amount of capillary non-perfusion in the retina? And the idea was that if there are processes in the brain, these processes may be manifested also in the retina. So the population were children who had malaria retinopathy, and they were also comatose. The design, it was a prospective observational study. It was done in Malawi. And AI was involved in denoising and deblurring, but this was not deep learning. this was actually a texture-based segmentation, which is one specific area of geometry and topology. And then after that, the texture-based segmentation was used to find the boundaries of capillary non-perfusion. And after that, we divided the retina into several sectors, of course, the central sector and also the peripheral sectors. We had 24 sectors going all around. And in each of the sectors, we calculated the proportion of capillary non-perfused pixels. And then we applied a statistical modeling, something like a linear regression model, where we wanted to check whether there is an association between the number of capillary non-perfusion that we see and the fact whether the child survived or died, and we did confirm the association. So that was one example. The other example is something that I mentioned last week, is AI can be actually used in a diagnostic type of studies. So the design would be a diagnostic study, and the question would be, okay, once we have an image of the retina, the color fundus image, how can we tell whether this belongs to an eye that has glaucoma? So you can either use deep learning to do that in one step, or like we did in this study, we actually processed in several steps, starting with segmentation, where we use deep learning, and then there was feature extraction, modeling, statistical modeling, and then we derived the probability of glaucoma. So there are some different types of designs, and to be complete, I did also decide to put here this pyramid of evidence, which is something that we always should have in our mind when we are reading papers. And that is a pyramid that says that different types of clinical designs of the study will give a different strength of the evidence. And as we go from the bottom, which is the background information and expert opinions, individual case reports, case series, cohort studies, and then we are moving into studies like non-randomized controlled trials, randomized controlled trials, all the way to meta-analysis. We are moving towards studies that are bringing stronger and stronger evidence towards using the results in the practice. So that's good to know. And it's always good to check in the paper that you read what design they are using and is it clear. Also, what is important to know is what is PICO or PICO-TS, which is something that helps me to understand the population. What is the population of patients that is in the paper? Is it clearly defined? Inclusion, exclusion criteria. Then INC stands for intervention and comparison. It is typically for studies where an intervention is studied. So this can be typically in randomized controlled trials, but of course it can also be in observational studies or in electronic health records, but they would have lower evidence, as we saw in previous slide. Outcome, is the outcome clearly defined in the paper? So outcome can be, is it glaucoma or not? Or did the child die or survived? What is the timing and duration of the study? Is it clearly defined? And also, is study type clearly defined? So it is very good to think in terms of this, because if the paper is not clear about this, then probably you are not looking at a good quality paper. Now I'm coming to the slide, which is again quite busy, but it is very important. And that is, again, how do I assess methodological quality of paper that has AI in it? And what are the main interrogation tips? And the main interrogation tips are around the sample size, which is how many patients are in each group, in the group that have glaucoma and they don't have glaucoma. The sample size is very important because, of course, if it is too small, then the study may be inconclusive. Sometimes sample size calculations are not possible to do, but if they are possible to do, that needs to be stated. And of course, every design of the study and every different way how we analyze the data comes with a different sample size calculation. If some groups are underrepresented, for example, if glaucoma group is underrepresented, then depending on what AI is being used, there may be a risk of bias in a sense that the group that is more represented may have a bigger weight on the final solution. So there needs to be some explanation in the paper how this has been mitigated for. And also Ivo will talk about it a little bit. The other tip that we need to look at is missingness. It is a topic that is not actually very as frequently discussed as I would like to, but it's a very important topic, and that is, are the authors reporting any missing data? Meaning, were there any patients for whom the color fundus photograph was not available because it was maybe lost, or maybe it wasn't able to provide with a good enough quality, maybe because of the cataract? If this is the case, then again, if there are some missing data, this may lead to a bias, especially if the missingness is not random. And again, the question is whether the paper is showing any mitigation, anything that they have done around the missingness. Are they testing whether the missingness is possibly non-random? So is there any structure to it? And if there is some structure to the missingness, if some data are missing because the patient has glaucoma, if there is a link, then definitely this is a very risk of bias. And some of these topics are also discussed in this book chapter that we published with Katie Barnes recently. Another important interrogation topic or tip that you need to think about is about how validation has been done. But this is only relevant to diagnostic studies. Did they report what is the reference standard? So for example, in glaucoma, what is the reference standard? How was it achieved? Was it one doctor who interrogated the color fundus photograph, or did they also use optical coherence tomography, or did they also use visual fields? And was it two doctors? And was there also a third doctor who would come on board if the two doctors don't agree? So this is very important to check, because, and I think this is actually the most important component of all three, I think. Also, what type of the validation has been done? Was it internal or external? What are they reporting? Are they only reporting sensitivity? That's not good. They definitely need to also report specificity, but they also need to report values like negative predictive value and positive predictive value. And also Ivo, later after me, will be talking about this. And also important is, if in the study they are doing measurements in several ways, and they want to see whether there is agreement between them, what method was used to establish whether there was agreement between measurements? And that should be typically by Blunt-Altman measures of agreement. So when we want to assess or read a paper, we also need to think about, did they use the right design? And we need to think about, do we understand what is design? So if the research question of the paper is about therapy, typically this is done by using a randomized control trial. So this is a preferred study design. If the research question is about diagnosis, like glaucoma, the preferred study is a cross-sectional study, but it can be also randomized control trial. If research question is about prognosis, then of course you need longitudinal study, because you want to know what is the prognosis of the patient if the patient is left untreated. And if the research question is about correlation as to, like, for example, the capillary non-perfusion study, the preferred design would be a cohort, prospective, preferably, or a case control study. Also in the diagnostic studies, like it's my second bullet point, typically what we want to know is whether a test is reliable and also valid. So here is an example of what we mean by reliable and not valid. So for example, this first bullseye pink plot is showing a reliable test but not valid. So this is like a picture explanation as to what we mean by reliable but not valid. Means that it gives results that are quite precise, but they are actually not accurate. And as we go all the way to the right, this is depicting a scenario where we would have a test which is both reliable and valid, because it does not have high variability, but is also accurate. Another important tip is when you are reading a paper, it may be quite overwhelming. I already gave lots of information, and on top of it, there is also AI in it. My recommendation would be, don't be overwhelmed, and see whether there are any guidelines that are official and that are published. And this is exactly what I'm using. And there are three main guidelines that I use, but there are more of them. And one is guidelines for randomized clinical trials. They are called consort guidelines. Then there are guidelines for observational studies. They are called strobe guidelines. And also there are guidelines for diagnostic studies. Why do I use them? I use them because they give very practical list of things that I need to look for in the paper in order to judge whether the paper is a good quality paper, whether I want to use this paper for my own understanding, or whether I want to assess this paper as a reviewer, or when I'm writing my own paper, of course, too. So here is the network called Equator Network, and they are listing here guidelines. These are the main guidelines, the blue one, but then when you see here, there are another 431 reporting guidelines that are not on the screen. And I also circled these diagnostic prognostic studies guidelines that are called START. And this is how they look like. When you click on it, it will tell you some history about these guidelines. And when you click on it further, it will give you a list of things that you need to check when you are reading a title, when you're reading abstract, etc. So I will not read through that, but I very much welcome you to check this. And also on the same website, there is also a diagram, a consort diagram, that is showing how the patients should be reported in a diagnostic study. And all you need to do is to fill in the numbers here. So this is where I will stop. So in summary, the main key points are that you should know the main principles. And the first main principle is make sure you understand what is the research question of the paper that you read. And then also know where to find guidelines. There may be guidelines for the paper that you are reading. When it comes to papers that contain artificial intelligence in it, well, I checked this morning this Equator Network, and I also checked these 431 papers in the list, and I didn't see AI paper in there yet, but I have a feeling I have read and seen there are papers being published where people are suggesting as to how the reporting should be done in AI studies. And but these papers that are being published, they are not yet incorporated into these guidelines, but it's probably just a matter of time. And I will stop here. Thank you very much.
Thank you, Gabriela. That was a very crisp introduction, how you should approach. I mean, it applies for every paper, but more so for papers with artificial intelligence. It's so important, especially the slide where you said, what are the different trials you have to do for different conditions. It was really very useful. Thank you, Gabriela. We'll take the questions at the end of both the talks. So next we have Dr. Siekmann, who's got his PhD in mathematical epidemiology at the University of Osnabrück, Germany. And he has worked across the globe from Australia to US to Germany. And finally, now he's the senior lecturer at the Department of Applied Mathematics at Liverpool John Moores University. He's got a lot of expertise. Some of them are even very difficult for me to pronounce, from Bayesian statistics using Markov chain Monte Carlo techniques to biological systems. I'm sure he's working on the pandemic COVID-19 also now. I'm sure you can give a few things if you're doing some work related to that and AI. But his main topic would be, what validation do you expect in an AI paper, and what are all the critical things we need to review, especially in eye care? Welcome, Dr. Ivo Siekmann.
Thank you very much for the kind introduction. So I will now talk about a more special topic. So Gabriela has given a general overview how to assess an AI paper, and I would like to specifically look at how to look at one aspect, validation of the methods that were used in the AI paper. So when we look at this, I would first of all like to explain how in general AI methods are assessed. So when you look at statistical methods, they are usually relying on mathematical theories that define how a specific model should work. And the statistical theory then guarantees why a method should work in a particular context. Now, artificial intelligence methods, machine learning methods, they have methods that are defined in a slightly more flexible way. So they start from the point of view that a good method may just be based on approximating how the data behaves. And in this way, you can handle even data sets where a particular theory is not so easy to find. This also means that these methods have to be evaluated slightly differently. So usually in machine learning, methods are evaluated using an experimental approach or an empirical approach. So what you do is you take known test cases. So we have test cases where we know, for example, in a health context, if a patient is healthy or sick. And we can find a very simple way to assess the performance of a method by just saying how many cases have we predicted correctly. So when we have a healthy patient, have we predicted this patient as healthy? If we have a sick patient, has this been done correctly? And how many have been predicted incorrectly? So a healthy patient that was predicted as sick, or a sick patient who was predicted as healthy. And the question is, why does this work? And the answer is that we hope that when we look at the performance on these test cases, that this actually reflects the true performance of the method. And we will look at some examples, and we will see when this hope is justified and when it may not be justified. So to look at how many cases we got right and how many cases we got wrong, we usually represent this in a structured way. So we use a method called the so-called confusion matrix, and this is what a confusion matrix looks like. So we have the predicted cases in our rows and the actual cases, so the true cases, in our columns. So the numbers we put in this matrix are determined as follows. So on the upper left, we have healthy patients that are actually predicted as healthy. And here on the upper right, we have sick patients that are predicted as healthy. So this is one type of mistake. On the second row, we have patients that are predicted as sick. So here we have healthy patients that are predicted as sick. So we have made a different type of mistake here. And on the lower right, we have sick patients that are predicted as sick. These type of entries in the confusion matrix are called the true negatives, the false negatives, the false positives, and the true positives. And based on these numbers, we can assess how well a machine learning method works. So when we look at a specific example, we see here that we have a data set where we have predicted patients as healthy and sick. And for example, here we see that 21 patients who are predicted as healthy were actually healthy. And 2 patients that were predicted as healthy were actually sick. So we have made a mistake here. And on the second row, we see predictions as sick and the actual outcome. So here we have got 3 patients wrong. So patients that were predicted as sick that were actually healthy. And we got 22 sick patients right. So when we want to get an overall measure how well we did, we can calculate the accuracy. And the accuracy is simply looking at the total number of examples that we got right. So we have 21 healthy patients that we found correctly and 22 sick patients that we found correctly. And if we divide the sum of these two by the total number of patients, we see that we get 22 plus 22 correct predictions, which gives us 43. And in total, we have 48 patients. So the overall accuracy is 89.6%. So in 89.6% of all cases, our predictions were correct. Now, the overall accuracy is something that is good to know, but of course, in detail, there might be more specific questions that patients might be interested in. So before a patient lets an AI method determine if they are healthy or sick, they might ask questions like, well, I'm worried that I am sick, and how likely is the AI method going to detect that I am actually sick? So here I make the assumption that I am sick, and the question is, how likely is it that the AI method is going to confirm this? This quantity is called the sensitivity, and I will show on the next slide how we can calculate the sensitivity. So of course, you can also be a more optimistic patient. You can say, okay, I am quite sure that I am healthy, but how likely will the AI method give me confirmation that I am healthy? And this quantity is called the specificity. Now, when we look at our example, we see that we have predicted 21 healthy patients as healthy, but in total, we have 21 plus 3 patients that are actually healthy. And this is the specificity. So we have to calculate the proportion of healthy patients that were predicted correctly over the total number of healthy patients. So we have 24 total patients that were healthy in our sample. And when we divide 21 by 24, we get 87.5%. So in this case, we have a high specificity. So we get a relatively large number of true negatives. So the proportion of sick patients that were predicted correctly are the true positives that we find in our data set. So here we look at the number of sick patients that were actually predicted as sick. These are 22. And again, we have 22 plus 2 sick patients in total. And we get 22 over 24. So this gives us an even higher number. So we get 91.7% of sick patients that were predicted correctly. Now, this is the overall approach, how we determine how well our AI method performs. But the question is, and this is very important, how these numbers are actually calculated. And this is what I'm going to look at in the next slides. Because when we look at validation, there are different ways of doing it, and not all of them are equally good. So let's say that our data that we looked at looks like this. So we have green points that are healthy patients, and we have red points that are sick patients, and we try to separate green and red points. And we do this in this example by drawing a line between the red and the green points. And we say that everything on this side of the line is classified as healthy, and everything at this side of the line is classified as sick. So what we see here is that we have 3 sick patients that were accidentally classified as healthy, and we have 2 healthy patients that were accidentally classified as sick, just in our numerical example above. The problem is that we have validated this AI method with the data that we have used for fitting. And our line depends on the data points that we have used, of course, so it will always be slightly biased by the data we have used for fitting. So the accuracy is usually overestimated if we do it in this case. So in practice, what you usually do is you try to do your validation with different data than you use for fitting your AI method. And I will demonstrate this approach on this slide here. So when we have a data set, we typically try to split the data set into 2 halves of approximately the same size. And one half is called the training sample, and one half is called the test sample. And when we split the data in these 2 halves, then in our training sample, we can use the data for fitting our method, and the test sample can be used for testing our predictions. Now, the advantage of this is that the test sample played no role in fitting the model that does the prediction. So the advantage is that we have, in a way, simulated the way of using our method for unseen data, and this should improve our accuracy estimate. So I would like to illustrate again with the same toy example how this works. So here we have our data set that we have seen before, healthy samples and sick samples. And now we just remove some of the samples and use them for forming test data sets. So the light green samples here are healthy patients that are not used for fitting our model anymore. And we take away also sick patients that are not used to fit our model anymore. So we remove them, and now we fit our model again. And what we see here is that the model has 1 healthy patient that is incorrectly classified as sick, and there is no mistake when we look at sick patients. Now, the idea is that you compare this performance on the training data set with the performance on the test data set. So now we bring the test data set back in. And when we look at the test data set now, we see that we actually have a different picture. So we have 1 healthy patient that is incorrectly classified, but we have 3 sick patients that are incorrectly classified as healthy. So we see that our error has slightly increased, and this is usually the case if you split your if you split your data in a training and a test sample. And the reason is that your training data doesn't really bias the model that much anymore, and the test data simulates the effect of having really new patients that we assess with our method. Now, the question is, what does this help? Well, the thing is that it's not so much about just the accuracy in itself, but the question is, how different is the accuracy? So when we have one accuracy on our training data that is quite high, and then we get an accuracy in our test data that is quite low, then we usually should get suspicious. And I will show on the next few slides why that is. So the next slide is also going to show why it is not always good to approximate the data as well as we possibly can. So we might get the idea that we want to get really good at maybe predicting healthy patients. So instead of using a line to separate healthy and sick patients, we use a curve. So we have a blue line now that is very close to the healthy patients and predicts very well how, if a patient is healthy. Now, when we look at this training data set, we see that we have 100% accuracy. So we have predicted all healthy patients accurately. We have predicted all sick patients accurately. And this all looks very good. So we have 100% accuracy, 100% sensitivity, 100% specificity. Now, the question is why this might not really be good. And this becomes quite obvious when we look at our test data again. So when we look at the test data, we see a completely different picture. So now we see that there are actually quite a few healthy patients that are now on the half that should be classified as sick. So we have incorrectly classified a lot of healthy patients in practice. So a lot of patients now would get worried because the method tells them that they are sick, although they probably aren't. So the message here is that if you compare training and test data, you can identify a problem called overfitting. So machine learning methods base their performance on approximating the properties of the data. And if they approximate the data a bit too well, it can be that they are really only performing well on the training data, but not on any other data set. And this can be identified to some extent if you have a training and a test data set. So now one other thing that we might be interested in is look a bit more at sensitivity or specificity, because we might find it very important to identify if someone is sick, but because we can follow up patients that are incorrectly classified as sick, we might be okay if we have a high sensitivity and at the same time a relatively low specificity. And to represent this, we use a method that is called the ROC curve, the receiver operating characteristic. And this curve plots 1 minus specificity against sensitivity. And first, I would like to show that we can actually always get kind of a good specificity and sensitivity if we do a very simple thing. We just guess. We have only two possibilities. We can classify someone as healthy and we can classify someone as sick. We could say that our method is only based on guessing. We just say randomly, okay, you are healthy, okay, you are sick. And when we do this, we say, okay, if we have 50% people classified as healthy and 50% classified as sick, we will approximately always get 50% right. So we will be on this point here. And you can see that it is even easier to get a high sensitivity if we want to be absolutely sure that we classify all sick patients correctly, we can simply say, okay, 100% of our patients are classified as sick. So we get, of course, 100% of them right. But that means that we also classify 100% of the healthy patients incorrectly. So this diagonal is not what we want to do. So the hope is that our method is doing better and gets slightly above or even much higher than this diagonal. And this pink curve is an idealized ROC curve that shows that when we here have a specificity of 50%, then we have a sensitivity of 80%. Now, usually methods have a trade-off between sensitivity and specificity. So if we want a really high specificity, so we want to be really sure that we don't worry anyone, then we move in this direction. So we accurately predict if someone is healthy, but that usually decreases our sensitivity. And in practice, you can decide if you either move somewhere here, so you have a method that is quite specific but not very sensitive, or you move here, so you try to be very conservative in assessing someone as sick, but you get the risk that more people are classified as sick incorrectly. And you can also go for somewhere in the middle, then you get the best of both worlds. You get the best sensitivity and specificity with the method you are using. So this is an idealized ROC curve. So for our example, it looks a bit more, ugly, not like a curve, but like a step function. But the principle is the same. So you can define the points that you are interested in, and you can tune the method by saying, okay, I want a high specificity or high sensitivity, or the best of both. So in summary, when we look at sensitivity versus specificity, there is a trade-off between the two, and we can tune our classifiers to be either very good at detecting sick or for determining healthy patients, or we can decide to tune our method to be reasonably good at both. Now, there's another thing that a patient might want to know, but we will see that it is harder to help patients with that. So now we are looking at a patient who has got a result from an AI test. And the AI method has predicted that the patient is sick. So the patient is a bit worried. He says, how likely is it that I really am sick? This is called the positive predictive value. Then there is a pessimistic patient. The AI method has predicted that the patient is healthy. And now the patient asks, how sure can I be that I'm really healthy? Now, this can also be calculated when we look at this confusion matrix. So we have here healthy and sick patients. So when we look at patients predicted as healthy, then 21 patients were predicted as healthy, 2 as sick. So when we look at this, we now have to divide 22 over 23. So we get 91.3% of predictions were in this case correct when we look at the healthy class. And we can do the same thing for sick patients. So the positive predictive value says that we have 22 patients classified as sick correctly. In total, we have classified 25 patients as sick. So in total, we get 22 over 25. Now, when we look in practice, I said that it is not easy to achieve this. In practice, often we have many more examples for healthy patients than for sick patients. So here I have simply multiplied the numbers in the healthy class by 100. And now we see a problem that the positive and the negative predictive value actually depend on the numbers of samples that we have in each class. So when we look at the patients that are predicted as sick, we see that we have still 22 patients predicted as sick. The problem is that in total, we had to predict many more patients, and 300 patients, if we assume the same error rates as before, have predicted as healthy, although they were really sick. So we see that the positive predictive value in this example is very low. Same thing here is that when we predict someone as healthy and the patient is actually sick, this does not happen a lot because sick patients are not very common in the population. So what you can see here is that you get a very high negative predictive value, and both these values are basically just a result of the fact that you have a much larger number of healthy patients in the population. Now I would like to close with showing something that gives you even better estimates for the performance of your AI method, and that is so-called external validation. So I said that typically you simulate using unseen samples, and you do this by splitting your data in a training and a test data set. Now we show something that is even better. Let's assume we have a different data set, maybe from a different clinical trial, and we keep away this data set and use another data set for training our method. So again, we train our method using our training data set, and then we apply the method to a slightly different data set from another sample. And what we can see here is that maybe this other sample is basically very similar, but we see that it has a slight bias. So you see that in this data set, you have slightly more patients that are above that line than below that line, and that will introduce a bit of an error. It can even get worse, and that would indicate that we have completely missed something. So it might be that we have actually a class of patients shown here on the upper right that we didn't have in our training data set at all, maybe because they have a different type of the disease. And all machine learning methods rely on working based on examples. And if we have something that we didn't see any examples for, it is not possible to really classify them correctly. So here you see a number of samples that are in the second data set that are completely missed because they could not really be used in the training data set. So I would like to summarize. There are 4 quantities that are used to assess the performance of an AI method. So we have the sensitivity, the proportion of the sick patients detected correctly, the specificity, the proportion of healthy patients detected correctly, the positive predictive value, which is the total number of patients that are predicted as sick that are actually sick, and the negative predicted value, so the patients that were predicted as healthy that are actually healthy. This is apart from the overall accuracy that you can also calculate. Now, I would also like to say that when you look at these numbers, it is important how they were found. So when you look at internal validations, the problems that can be identified with internal validations is, for example, the overfitting problem. But in practice, when you have new data, external validation would be quite valuable because external validation will also show you things that are genuinely different in true data because they didn't appear in your test data. So for example, here you have a slight bias and an additional population, so you would also be able to detect this. And with this, I would like to thank you very much for your attention, and I'm happy to reply to questions.
Thank you, Dr. Siekmann. I think it was you made it so simple and so easy for even the beginners or even the advanced people to understand some of the important aspects. Now, it applies generally to any paper, but more so for AI paper. The importance of sensitivity, specificity, the positive predictive value and negative predictive value. Thank you again, and we'll open up to the panelists for any questions. Can you close the screen, Dr. Siekmann?
Yes.
Any questions? You can unmute and ask the questions to either Gabriela or to Siekmann.
I think there doesn't seem to be questions. I don't see them in Q&A or chat.
Yeah, there's no. I don't see any
Yeah,
questions.
maybe we were very clear.
Very.
Yeah. I'm very happy that Ivo gave very simple example.
Yeah.
So that people can actually see on a very simple example how these numbers work out together. Because once they understand that, they can go and read the papers. Yeah. And also what I would like to say is when you read papers, sometimes people use the term sensitivity, specificity, positive predictive value, negative predictive value, but sometimes they use slightly different terms. They would use the word precision and also recall. And now can Ivo remind me what is precision and what is recall?
So precision is sometimes used for positive predictive value. So the idea is how precise are your predictions?
Mm-hmm. And
so,
the recall?
Recall is sensitivity. So how many of the patients you want to identify, how many of the sick patients can you recall? So how many can you find? So this is the idea behind these.
So there is unfortunately a little bit difference in how people communicate when they write papers. So they may use different terms. Also, the term accuracy is not something I learned when I was in my school. I studied statistics. What I learned was something called total proportion of correctly classified, which I find more intuitive to understand. But so the total proportion of correctly classified is what Ivo called accuracy. So that's just a little warning that sometimes people use different terminologies.
Gabriela, there's a question from Mr.
Yeah,
Ganesh.
so I found there was a question on k-fold cross-validation, and I think I can answer that. So you could say that cross-validation is in a way repeating the sample splitting method again and again. So the problem is that when I do sample splitting once, I get only one estimate of my sensitivity, specificity, and whatever I want to calculate. If I do k-fold cross-validation, I do this repeatedly. So I use different training sets because I select different parts of my training data as the training set. And I use different test sets as well. And by repeating this k times, I get not just one estimate, but k estimates of sensitivity, specificity, accuracy. And this is, of course, when you do things experimentally, empirically, using statistical methods, it is always better to have more data. So the idea is that you are better at estimating sensitivity and specificity. Maybe our first test data set was just really different to the training data set. It was something that was too pessimistic. Then we might have a test data set where we got really lucky and we get a really good performance. But by doing this k times, we, in a way, average over these random problems.
Yeah, exactly. And not only you can average across all these K sensitivities, you also know the range of sensitivities you can get from the smallest to largest. So this, in a way, gives you information on what the confidence interval might be for the sensitivity. And in the paper that we published on glaucoma, we did a different thing. We did random splitting 100 times. So again, 100 times we get sensitivities, 100 sensitivities. And then from that, we could get confidence interval. Or we could get what is the standard deviation of those sensitivities. So this gets you, the standard deviation of those 100 sensitivities gives you how precise you are in the estimate of your sensitivity. Yeah.
Yeah. So there's another question now. What should be the acceptable accuracy for deploying AI safely?
This is a very difficult question. I don't have a definite answer. I would say this depends on what it is going to be used for. If this is going to be used for screening, then you may be allowed to have a lower accuracy because then those patients will go for a further test. But if it is going to be used for a definite final diagnosis, then accuracy must be much, much higher. Also in Britain, for example, for diabetic retinopathy, for screening, there is a rule that the screening program should have at least 85% sensitivity. Okay, but this, of course, can lower your specificity. So in a case, you may then, of course, look at lots of patients who do not have diabetic retinopathy later. So sometimes it's not about maximizing the accuracy, it's about what are the national guidelines in terms of what should be the minimal sensitivity. But it's also about what it is used for. Yeah.
I think previously also we touched upon this. No, when you are trying to develop an algorithm, you keep in mind, like for example, glaucoma or DR, the fundus cameras, the quality of the cameras, the quality of the imaging. Now, so many variations are there. Now, how do you deal with that when you are analyzing and writing it up?
Yeah, the quality of camera, the type of population, the actual processes that each hospital has in terms of acquiring images and then storing them, what protocols they have, that everything can bring another variability into data. And therefore, if you then want to evaluate accuracy of AI in a different hospital, the accuracy, the area under the curve will drop down a little bit or a lot. So I would say you need to, personally, I would say, rather than using AI immediately, ideally, you should test it on your own data, how it is fit for the purpose in your hospital or in your clinic.
To add to that, I think that was a very good question because generally, I think even not just in medical imaging, a lot of other areas as well, there's a huge gap between research and actual deployment. So research paper, we quote very high accuracies, 96, 99. But in real life application, it has to work in a lot of areas where it doesn't. So when usually like big companies like Google and et cetera, who are actually going to make money out of actually deploying it, they try to collect a lot of data from different places so that they have a general. So for example, if it has to be fundus, the training data set should have images from almost all of the machines so that it considers the variation in pixel. Because for example, Remedio's camera has a different quality of pixels compared to higher end Topcon images. So when a deep learning model is trained on just a Remedio image, it will not predict any, it won't work on a high-end Topcon image because the pixels are completely different. So in these cases, the training data set has to have these various, amount of images or various images from a lot of machines before ending up in an actual deployment. And that's a huge, gap between research paper and actual deployment. So in an actual deployment, any AI work needs a lot more, data and a lot more work before actually deploying it.
That's a very valid point. Yeah, I agree. So maybe one way to do that is that whatever data are in electronic health records that are collected routinely are collected in such a way so they can be readily used by AI once, of course, the ethics is being done and everything.
Very true. The EMR should be rather, AI user friendly for us to, pull data easily and train on top of that as well. Yeah.
I think this we touched upon the last session. Now there's Dr. Saravana Bava asking difference between internal and external validation.
Yeah.
Gabriela, you just want to highlight quickly?
No, I think we said it all when it comes to this question. Yeah.
I mean, you can say that what the previous panelist asked, when you have a big data set that contains all possible camera types of fundus images, this is something that you would be able to pick up with an external validation. So when you have trained your model with just one type of camera, and then you have a data set from a different camera, you will see that your performance will drop quite a lot. But if you have just internal validation, so if you have your training data from one camera and you split in training and test data set, you will see that you might actually not get such a drop in accuracy because your method is good at this particular camera. It just doesn't include examples for all different cameras. So this is what my simple example tried to illustrate using the additional population. If you have unseen examples that are genuinely missing in your training data set, this is something that you could pick up in an external validation. So if you apply your method to many different contexts, you might discover that in some contexts it doesn't work anymore. And one reason might be that the examples are simply not part of the training data set.
That's very important. And also, not only a different camera, but also in your hospital clinic, you may have slightly different composition of patients, or you may have another type of patients that hasn't been in the original training data set. So that can be also a reason when algorithm validation on your data may drop because there are some patients that haven't done before.
Yeah.
So this is one of the things that AI does. It will always tell you how likely AI thinks it is glaucoma or not. It will always do it. The question is it correct or not? So the validation is extremely important. And these days, there are groups who start look also into how certain the artificial intelligence is. So there is one paper that I listed last week by Liebig. They looked at not only what is the probability of referable diabetic retinopathy, but also how certain the AI is.
Thank you, Gabriela. Again, and also this time we had a very, very special talk from Ivo Siekmann. Again, we sincerely appreciate and thank him for joining us today. And the last session will be on 23rd July. And again, it's going to be interesting where we are going to focus on general ophthalmology beyond glaucoma DR. We are also seeing at age-related macular degeneration and other applications in conditions like CSR and other retinal problems. So please join us next week, same time, next Thursday, Indian time, 5 to 6 p.m. Thank you.
Thank you.
Thanks a lot.